Europa orbits within a storm. Jupiter tears at it with gravity stretching its crust until the ice screams, and the oceans below boil in secret. Here, heat is born from violence, a constant war between freezing silence and tidal fire. What we see from afar is serenity, a gleaming sphere of white, but beneath the crust moves the water churns and chemistry rebels against extinction. For 4 billion years, this world has been quietly alive with motion tides, minerals, pressure, and time. If life has found a way to survive in that abyss, then the story of biology does not belong to Earth alone. Right now, let us begin our descent through the silence past the frozen crust, where secrets long kept in darkness are waiting for us to find them. Far beyond the warmth of our sun, Jupiter reigns like a silent monarch. Its pale light spills across its moons, painting them in silver and amber. Among them drifts Europa, a world so bright it looks almost alive. From the first images captured by Voyager 1 and 2 in 1979, Europa appeared like a mirror carved from ice. No mountains rising, no deep shadows, only a smooth, glimmering crust. Its surface reflects more sunlight than any other moon in the solar system, more than Earth's own moon. To the instruments of Voyager, it seemed motionless. Yet too young, too perfect, as if the scars of time had been erased. Scientists soon realized what that meant. Cratering is the clock of worlds. The fewer the craters, the younger the face. Europa's near absence of impact scars revealed something extraordinary. The surface was being renewed. Somewhere beneath that frozen shell, a force was at work reshaping everything above it. Imagine flying over it now. You would see wide streaks of brown and red stretching for thousands of kilometers, ancient cracks sealed with darker ice. They look like veins under translucent skin faintly glowing in Jupiter's reflected light. Each one records an episode of tension and release as the crust fractures and then freezes again. Only the invisible pull of Jupiter itself, tides so strong they flex an entire moon. That motion repeated over eons may have melted the layer below. So Europa gleams not because it sleeps, but because it breathes beneath the ice. Every shimmer we see from Earth may be the echo of movement, a quiet heartbeat beneath a frozen skin. Seen from a distance, Europa looks immaculate, a pearl orbiting in Jupiter's glow. But as spacecraft drew nearer, the illusion of stillness broke. The ice was not untouched. It was scored, fractured, stitched together by scars that stretch for thousands of kilometers. They are called linear, long, sinuous lines etched by forces deep within. Each line tells a story of stress and release. Jupiter's immense gravity tugs at Europa, squeezing and stretching it like a living thing. The ice groans, fractures, then freezes again. When sunlight glances across these lines, they shimmer like veins of bronze beneath glass. Some run straight, others twist and braid into tangled networks, marking places where the crust has torn and shifted. Imagine standing there. Under your feet, the ground would be solid but faintly trembling as if something vast moved below. The silence would be total, no air, no wind, only the low hum of a moon under strain. Each crack could open at any moment, releasing ancient frost, whispering vapor into the void. Scientists believe these fractures are keys to the moon's hidden machinery. Spectral analysis from Galileo and Hubble found salts and frozen compounds along their edges, traces of material that once came from deeper layers. It suggests that the surface and the interior are not isolated. They talk to each other through these channels of pressure and time. What we see are not scars of destruction, but pathways of communication, the surface answering the tides of its parent planet. If Europa were truly dead, its face would be littered with the wounds of impact unchanged for billions of years. Instead, it appears restless. A world still reshaping itself, rewriting its own history in lines of ice and mineral. And so beneath that quiet exterior lies motion. Every fracture a sentence, every ridge a breath. The moon that seemed frozen solid may in truth be alive, not with creatures or forests, but with movement itself, the slow pulse of a hidden ocean, urging the ice to move again and again under Jupiter's eternal gaze. The more we studied Europa, the clearer it became. Its surface is not ancient, it is renewing. No other icy moon shows this balance of perfection and disruption, order and fracture. When Voyager first sent back its blurred images, the smoothness seemed ordinary. But high-resolution maps from Galileo changed everything. The lines did not lie flat, they crossed, collided, and overlaid each other like sheets of glass that had been shattered and refrozen. To a geologist, this meant something remarkable. The crust of Europa behaves like a giant raft of ice floating on a liquid or semi-liquid layer beneath. When Jupiter's tides stretch, it cracks form. when the stress releases those cracks close and seal with fresher frost. The cycle repeats endlessly, break, drift, heal. It is cryogenic tectonics, a cold echo of the processes that shape Earth's crust. In the chaos terrains, the surface buckles into jumbled plates, tilted and rotated as though the ice had melted locally, then refrozen in confusion. Some blocks are kilometers wide. Beneath them, scientists suspect pockets of warmer water rising from below short-lived seas that briefly touch the surface before freezing back into silence. These are not random scars. They are signs of heat and motion proof that Europa's crust is still alive. Picture it from orbit, a sheet of white glass cracking under invisible tension, releasing faint glows of energy, then freezing again within hours. To the human eye, nothing changes. To a patient observer, the world is breathing. Each cycle may recycle minerals, carry oxygen downward, and push salts upward, linking surface and ocean in a slow exchange that could feed chemistry and perhaps biology. If we could watch for 1,000,000 years, we might see continents of ice drift vanish, reappear. But we have only moment snapshots in time, and even in those Europa whispers, its secret creation is not a single event. It is a rhythm, slow and persistent, written in frost and pressure. This moon rebuilds itself endlessly, as if trying to keep something hidden alive beneath its glacial skin. From afar, Europa seems frozen in eternal silence. Yet silence can be deceptive. Every orbit, as it circles Jupiter in a gravitational dance, the moon flexes its entire body, rising and falling by as much as 30 meters. No other world in the solar system endures such constant strain. That tidal rhythm is relentless. It stretches the crust, warms the depths, and keeps what lies below from turning to stone. Deep within, molecules rub, twist and collide. Friction becomes heat, and heat becomes motion. The ice responds slowly, bending like glass warmed by an unseen fire. To us, this movement is invisible, but its fingerprints are everywhere. The smooth plains, the fractures sealed with darker ice, the strange reddish hues born from salts pushed upward. Scientists believe this cycle of tension and release has lasted for billions of years, a heartbeat powered by Jupiter itself. Each pulse may churn the ocean beneath, mixing minerals from the rocky core with oxidants from the frozen surface. That circulation could make Europa's sea not just liquid but dynamic, a vast chemical engine operating in the dark. If you stood on the ice and listened, you would hear nothing. But under your feet, entire continents might be shifting, sliding, whispering. The moon's crust could rise and fall like a slow tide under a black sky, unseen yet constant. And somewhere below, where pressure meets warmth, water moves. Europa's stillness, then, is an illusion, a mask worn by a world in motion. Its beauty is not the beauty of death, but of balance, a frozen surface maintained by hidden energy, a planet-sized paradox where cold and heat, silence and motion coexist. The question now is inevitable: if such power exists beneath the ice, what else might be alive there? The deeper the cameras peered, the stranger Europa became. Across its surface stretched long, dark ribbons, lines that seemed to divide the moon like fractures in ancient porcelain. Scientists named them lineae. They run for thousands of kilometers, looping the globe in chaotic webs as though someone had drawn them with trembling hands of fire. Each line is not a scar, but a record of movement. As Jupiter's gravity pulls the ice cracks, as the moon relaxes, the fissures seal, leaving behind dark seams filled with material that may have welled up from below. Spectrometers aboard Galileo revealed that these regions contain salts, magnesium sulfate, sodium chloride minerals that on Earth form only where water once flowed. They tell us that the surface and the hidden ocean may be connected, however briefly, through these temporary wounds. Picture this: pressure builds deep within the crust stretches and a fissure opens. From the abyss below, slush and vapor surge upwards, spreading across the surface before freezing again. In moments, the event ends, and a new stripe is written across Europa's face, the geological equivalent of a heartbeat. To a spacecraft, these lines appear faint, but to imagination they are rivers of history. They may mark where tides once rose under ice, where energy escaped, or where life's ingredients could have found a passage. Each crack could be a door momentarily opened between ocean and vacuum. In the thin glow of reflected sunlight, the lineae shimmer. They trace the story of a world that refuses to remain still. When scientists map their intersections, they find patterns too deliberate to be random, an intricate network driven by internal tides. It's as if Europa has its own tectonic rhythm, colder but not less alive. So the lines we see from millions of kilometers away are more than frozen fractures. They are messages in ice written by motion, erased by time and written again. and each one seems to whisper the same truth. Beneath this intricate web lies something vast and ocean that may still stir in the dark. At first glance, the chaotic regions of Europa look like frozen storms. Fields of shattered blocks lie scattered across the plains, slabs of ice tilted at odd angles locked together like puzzle pieces that never quite fit. To planetary scientists, these regions are known simply as chaos terrains. To the human eye, they appear like continents caught in the act of breaking apart. Each chaos field is vast, spanning hundreds of kilometers. Radar and imaging from Galileo revealed that the blocks are not random. They seem to have drifted, rotated, and refrozen in new positions. It's as if an enormous lake of ice melted from below, loosened the crust, and then froze again before the blocks could settle. This is the language of movement captured in stillness, evidence of something warm, perhaps liquid, rising toward the surface. Scientists suspect that chaos terrains are places where heat from Europa's interior breaks through. They may form when pockets of water or slushy ice well upward, weakening the crust from beneath. When that happens, the upper layers fracture and float, drifting slowly before solidifying again. Such events could even recycle chemicals between the ocean and the surface, providing energy and nutrients to the dark sea below. Imagine hovering above one of these plains. Below you, colossal plates of ice glisten under Jupiter's faint sunlight, frozen mid-motion. Shadows fall into fractures that seem bottomless. What looks like stillness is only a paused moment in a slow geological tide, an instant in a cycle that may last 1,000,000 years. On Earth, we find a faint echo of this in the ice shelves of Antarctica, where frozen sheets break and slide atop liquid water. But Europa's scale dwarfs ours. Its chaos fields are planetary scars, reminders that even the coldest worlds can still move, still change. To look at a chaos terrain is to glimpse an ongoing process, creation disguised as destruction. Each fractured plane tells us that Europa is not passive ice, but active geology, a world sculpted from below by invisible tides. The frozen landscape hides warmth, and in that warmth the potential for life's chemistry to awaken. Every world has a heart. For Europa, that heart is invisible, a rhythm of gravity and motion that beats beneath layers of ice. It is powered by Jupiter itself, the giant whose pull twists and stretches this small moon every single orbit. Europa travels in an ellipse, not a perfect circle. That slight imperfection means that as it moves closer and farther from Jupiter, the force of gravity rises and falls. The moon flexes, compresses, and relaxes like a vast breathing organism. Within this constant strain generates friction. Friction becomes heat, and heat, even in the far reaches of the solar system, means the difference between stone and water. It's a process called tidal heating, the same mechanism that drives volcanoes on Jupiter's fiery moon Io. But where Io erupts in molten rock, Europa channels its energy through ice and ocean. Computer models show that this hidden heat could keep an entire layer of water liquid for billions of years. An underground sea warmed not by sunlight, but by gravity. Imagine it. An ocean locked in darkness, kept alive by the gentle kneading of an unseen hand. The energy flowing through it is immense enough to prevent complete freezing, enough to sustain currents that circulate minerals and salts. It could even fuel hydrothermal vents at the seafloor, where water meets rock in chemical reactions rich with potential. We tend to think of heat as fire, but here it is motion, the slow grind of tides that never rest. Europa has no seasons, no wind, no weather yet. It possesses a climate of its own, a balance between cold silence above and restless warmth below. This hidden engine is why scientists no longer see Europa as inert. It is a world in equilibrium, its surface sculpted by the invisible pulse of energy within. Every fracture, every dome, every chaotic plane above is an echo of this deep heartbeat. When you look at Europa shimmering beside Jupiter, remember it shines, not because it reflects light, but because something beneath it moves persistently, tirelessly, keeping a secret sea from turning to ice. Nothing on Europa lasts forever. Every fracture, every ridge, every chaos plane is part of a slow, repeating cycle: destruction, followed by rebirth. The ice cracks under Jupiter's pull, melts slightly, then freezes again in silence. New frost forms where old ice once stood, erasing ancient scars until the surface gleams like glass once more. Scientists call this resurfacing. It is Europa's way of healing itself. Instead of erosion by wind or rain, the moon's renewal is driven from within by tides, and temperature by the ceaseless struggle between gravity and cold. Each event may bury old chemistry and expose new salts, constantly rewriting the upper layers of ice. It is a geological heartbeat, one that never truly stops. To visualize it, imagine a planet covered by an ocean, but that ocean is frozen solid on top. Beneath slow currents of warmth push upward. The shell above bends, fractures, and repairs. In 1,000 years, a ridge forms. In 1,000,000, it vanishes again beneath new frost. Europa's landscape is not static, it flows through time, sculpted by invisible tides. What seems ancient is young. What seems quiet is alive with movement. Each smooth plain hides the memory of storms that raged not in air but in ice. And so, as the moon orbits Jupiter, it renews itself endlessly, a cycle without beginning or end. No world we've known behaves quite like this, a frozen face that rebuilds itself from within. That constant renewal hints at something greater. For if Europa can keep reshaping its skin for billions of years, then the energy inside it must be vast. Perhaps enough to sustain an ocean, and maybe the beginnings of life itself. In the 1990s, a spacecraft named Galileo arrived at Jupiter carrying a question older than its own circuitry: what lies beneath the icy worlds that circle the giant planet? For the first time, humanity had a messenger in that distant realm. Galileo orbited Jupiter for nearly 8 years, flying again and again past Europa, Callisto, Io, and Ganymede. But it was Europa that stole its attention, that smooth, bright moon that seemed too young, too alive, too impossible to ignore. Each close pass yielded new data, sharper images, magnetic readings, measurements of gravity. Every instrument told the same quiet story: Europa was not solid ice. Something heavy and fluid lurked beneath. From the outside, the spacecraft's camera saw lines and scars. Inside, its sensors felt the subtle tug of gravity shifting as it flew overhead, suggesting variations in density beneath the surface. That data hinted at a layered world, a crust of ice floating over something denser, perhaps an ocean or slush. The magnetic detector, a coiled antenna tuned to whispering fields, recorded something stranger still. When Jupiter's powerful magnetic field swept across Europa, the readings changed as though the moon itself were responding. It was as if Europa carried an induced magnetic field of its own, born from a conductive layer hidden deep below. On Earth, that would mean salt water. Scientists recognized the signature immediately: induction. Only a conductor could create that magnetic echo, and on a frozen world there is only one conductor large enough: a vast salty ocean. Salt water, with its charged ions, responds to magnetic fields, generating a weaker one in return. The equations matched perfectly. Beneath the ice, there had to be a global sea, not isolated pockets, but a single continuous body encircling the moon. This discovery transformed Europa from speculation to evidence. The crust was no longer an impenetrable barrier, but a thin veil, perhaps only a few kilometers thick in some places, floating on an abyss of water, nearly 100 kilometers deep. That would make Europa's ocean contain twice as much liquid as all of Earth's seas combined. Imagine that a world smaller than our moon, holding more water than our planet. A black, silent ocean stirred by the slow flexing of tides, untouched by sunlight for billions of years. No waves, no storms, only the slow exchange of minerals and energy between rock and water. As Galileo's data streamed home, the scientific tone shifted from cautious to awed. Europa was no longer a dead sphere of ice. It was a living system, dynamic, restless, breathing through its magnetic skin. The spacecraft had not just mapped a moon, it had uncovered a paradox. In the coldest place, imaginable warmth endured. And where there is warmth, there may be chemistry. And where chemistry persists, life might not be far behind. The revelation did not end with data. It changed the way we looked at the solar system itself. For centuries, humanity had imagined life as something that must cling to sunlight, to warmth, to air, to the fragile comfort of a thin blue sky. Europa defied that assumption. It suggested that life might not need the sun at all. If an ocean could survive beneath kilometers of ice kept alive by gravity instead of heat, then perhaps biology was not a rare exception, but a natural consequence of chemistry and time. The realization rippled through planetary science like a quiet detonation. Where else then might hidden seas exist? Enceladus orbiting Saturn showed geysers too. Titan had rivers of methane. Suddenly the outer solar system no longer looked barren. It looked fertile, not with forests or fields, but with potential. Europa had become the proof of concept for a new idea that life's true domain might be the dark, not the light. Hydrogen and oxygen, carbon and salt. The raw ingredients are everywhere. If even one moon can hold them in a stable ocean for billions of years, the odds shift. The cosmos becomes less empty, more inevitable. For the engineers and scientists of NASA, the discovery carried a different weight. It meant we had found a place worth returning to, a world whose secrets could be reached not by imagination, but by machine. The evidence Galileo uncovered became the foundation for future missions, blueprints for radar mappers, spectrometers, and probes that could one day taste the frozen breath of Europa itself. Yet beneath the equations and plans, a quieter thought remained. We had glimpsed not just another world, but a reflection of life's persistence. A reminder that existence adapts, that even in darkness, the ingredients of being keep moving. The consequence of Galileo's discovery was more than scientific. It was philosophical. It told us that the universe may be less about where life can survive, and more about how determined life is to exist at all. From the outside, Jupiter seems a world of storms, a giant shrouded in cloud and lightning. Yet its greatest power lies not in what it creates for itself, but in what it does to the worlds around it. Its gravity is overwhelming, a constant unseen tide that pulls at its moons like a heartbeat that never stops. Europa is caught in that rhythm. It does not orbit in a perfect circle. Its path is slightly stretched, an ellipse that brings it closer, and then farther from the giant each time it turns. As it moves, the strength of Jupiter's pull rises and falls, flexing the entire moon as though it were made of soft clay. No other planet exerts such influence. No other moon experiences such relentless strain. Inside Europa, that motion becomes friction. Friction becomes heat. And heat, even in the cold outer reaches of the solar system, becomes the spark of possibility. This is tidal heating, a quiet furnace that never burns out because it is powered by gravity itself. On Earth, our tides only stir the seas. On Europa, tides stir the planet. They twist rock, squeeze water, and create warmth in places where sunlight never shines. In the black abyss beneath the ice, that warmth keeps an ocean liquid circulating alive. Imagine a world without day or night, yet with an inner engine that never rests. Every orbit, every flex, every vibration feeds energy back into the crust like a cosmic breath, keeping the sea below from freezing solid. So the source of Europa's life may not be its distance from the sun, but its dance with Jupiter, a gravitational waltz that grinds, warms, and sustains. The largest planet in our solar system may also be the quiet creator of life's conditions far beyond its own clouds. The heat of Jupiter does not burn, it stirs, it needs. And in the frozen silence of Europa, that invisible fire may be enough to keep an entire ocean awake. Inside Europa, warmth is born not from fire, but from struggle. Every orbit, the moon bends and flexes under Jupiter's grip, a slow, rhythmic pain that keeps it alive. Rocks grind. Ice layers shear against one another. Friction spreads through the crust like an invisible pulse diffusing heat into the deep. In this quiet furnace, temperatures rise just enough to change everything. A few extra degrees can melt the lower layers of ice, turning them into soft, slushy water that drifts like glaciers in motion. Deeper still, that warmth keeps an entire ocean from freezing its surface, capped by a shell that groans with every tide. No flames, no sunlight, only motion becoming energy, gravity becoming heat. Scientists have modeled this internal ballet for decades. Each calculation reveals that Europa's interior could maintain a stable ocean for billions of years. The heat is strongest where the moon's orbit is most stretched, in the same places where its surface fractures and rebuilds. In those zones, water may rise and fall like slow tides circulating between ocean and crust. It is perhaps a world-sized experiment in endurance life. If it exists, there would owe everything to this subtle, ceaseless friction. Imagine drifting through that hidden sea. The ice ceiling above creaks faintly, glowing from Jupiter's reflected light. Below, currents swirl in the dark, carrying minerals and warmth from the rocky mantle. The entire ocean is a whisper of movement, never loud, never still. Friction is a simple thing, but on Europa it becomes creation. It transforms cold into possibility. Without it, the ocean would have frozen eons ago, sealing its secrets forever. Because of it, the sea endures, turning the moon into a paradox, a frozen world with a living heart. When we speak of heat, we often picture fire. But in the farthest reaches of space, heat takes quieter forms. The slow press of gravity, the sigh of tides, the patience of ice. And from that silence, warmth enough to sustain a hidden ocean, a world kept alive by the smallest movements in the dark. If Europa has an ocean, then warmth is not just its guardian, it is its heartbeat. Deep beneath the ice, far from sunlight, that heat becomes the first form of nourishment. It keeps water liquid, but more than that, it keeps chemistry alive. Without warmth, molecules sleep. With it, they begin to dance. At the boundary where water meets rock, the forces of Europa's interior come together. Gravity bends the crust, pressure squeezes the ocean floor, and minerals seep outward from the mantle. Here, heat and chemistry merge, creating potential reaction and renewal. It is a place that mirrors our own planet's beginnings. On Earth, in the lightless depths of the Pacific hydrothermal vents, spew minerals and energy into darkness. There, bacteria thrive without sunlight, drawing power from the chemical imbalance between water and stone. Around them, gather ecosystems of worms, crabs, and translucent fish, living entirely from the heat that rises from below. If such life can exist in our seas warmed only by geological breath, then Europa's ocean might not be so different. The model suggests convection currents may circulate through its depths, distributing heat and nutrients. Those gentle movements could create gradients, temperature, chemistry, pressure, the same conditions that on Earth led to complexity. It is the universal pattern of life's chemistry. Energy flows, imbalance seeks balance, molecules adapt. So when scientists speak of Europa's warmth, they mean more than temperature. They mean continuity, a system that has persisted since the solar system's youth, quietly maintaining the ingredients that define life. Imagine that ocean black as ink, soundless except for the low groan of ice, above the faint hiss of mineral plumes below. In that silence, warmth flows invisible and patient. Not the warmth of fire or star, but of endurance, a heat that has waited billions of years for something to notice. If life began there, it would owe its existence not to light, but to gravity's compassion, to a universe that even in its coldest corners finds ways to keep things alive. The evidence gathers like threads converging toward a single truth. Europa's ocean is not a fragile anomaly, but a system vast, ancient, and sustained by rhythm. Each flex of its crust, each sigh of heat binds the surface and the abyss together in an endless exchange. When tidal energy flows upward, the ice shifts and fractures. When it flows downward, minerals sink, feeding the sea below. This two-way motion, crust to core, core to crust, is the bridge between worlds. The surface gleams under sunlight, the depths glow with the residue of heat. Between them stretches an unbroken chain of cause and renewal. In that balance lies Europa's secret harmony. Gravity warms, ice shields, water endures. The three elements form a loop so complete that it almost feels deliberate, as though the moon has discovered its own method of survival. To scientists, this cycle represents stability, a place where liquid water could remain for billions of years. To dreamers, it is a whisper of life's persistence, the idea that warmth and water, wherever they coexist, will eventually try to organize into something that remembers. Imagine drifting down through the crust, through kilometers of glowing blue ice, past fissures frozen mid-motion, until you reach the dark ocean beneath. There the surface and the interior merge into one slow pulse, a rhythm that connects gravity, heat, and water in a single breath. Europa's bridge is not made of stone or steel. It is made of motion, chemistry, and time, a quiet pathway linking energy to endurance, matter to meaning. It is the bridge that leads from the mechanics of a moon to the possibility of a living sea, and through it the story of Europa turns from theory into wonder, the first glimpse of a world that might one day prove the universe is never truly cold. Far beneath Europa's glittering crust lies a world that never sees the sun. A vast hidden ocean stretches from pole to pole, a realm sealed in darkness for billions of years. No rays of light penetrate the ice, no dawn or dusk marks the passage of time. And yet, somewhere in that darkness, warmth flows, not in bursts, not in flames, but in quiet, persistent currents that never stop moving. This warmth begins where ice gives way to stone. At Europa's core, the pull of Jupiter flexes the solid mantle again and again like the slow breathing of a planet. Every motion grinds rock against rock, squeezing and twisting the minerals until friction becomes heat. That energy rises through the mantle, seeps into the salty ocean above, and transforms a frozen abyss into something alive with motion. It is not a violent heat. It is a patient one, spreading gently through the dark water, creating gradients, stirring chemistry. At the bottom of that ocean where the water meets the rock, a transformation unfolds. Pressure crushes everything to silence, yet here molecules awaken. Heat from the mantle drives chemical reactions between rock and water, a process called serpentinization, in which olivine and pyroxene minerals common in rocky bodies react with liquid water to produce hydrogen gas. That hydrogen, simple and abundant, is the spark that makes chemistry dynamic. It can combine with carbon dioxide dissolved in the ocean to form organic molecules, the very foundations of metabolism. On Earth, such places exist at the mid-Atlantic ridge, in the dark depths of the Pacific, where hydrothermal vents spew warm, mineral-rich water into the cold ocean. Their life thrives without sunlight, feeding not on light but on chemistry. Bacteria gather around those vents, harnessing energy from the reactions of hydrogen and sulfur. Above them, entire ecosystems bloom, tube worms, shrimp, crabs, all drawing life from a source that burns without flame. Europa's seafloor could be the same, only colder, quieter, older. Instead of black smokers that roar with superheated water, it might host vents that exhale softly, lukewarm plumes carrying minerals, methane and hydrogen upward into the darkness. Here the temperature might hover just above freezing, the pressure immense, the light absent. But energy still flows enough to power chemistry, perhaps even metabolism. Imagine descending into that alien ocean. The water is utterly black, the only light the faint bioluminescent glow of chemical reactions or drifting crystals, reflecting Jupiter's distant shimmer. The ice above is kilometers thick, filtering every vibration, every sound. You would hear only a low hum, the heartbeat of the moon itself, the tidal rhythm that feeds the deep. Now imagine the vents themselves, rough chimneys built from frozen minerals rising like cathedrals from the seafloor. From their mouths drift shimmering columns of warmth, carrying whispers of hydrogen and sulfides into the surrounding dark. Around them, invisible reactions unfold. Water meets mineral, mineral meets carbon, carbon meets energy. A slow choreography begins producing complex molecules that cling together, break apart and begin again. Each cycle, one step closer to what we call life. No one knows if Europa ever crossed that threshold. But the ingredients are all here, water, heat, chemistry time. 4 pillars strong enough to hold the weight of life's possibility. If biology is a recipe written by physics, then Europa's kitchen has been simmering for 4 billion years. Scientists believe that these reactions could sustain themselves indefinitely, so long as tidal heating continues. Even if the vents are rare, the chemistry can spread through convection, seeding the entire ocean with nutrients. In such a world, life need not thrive in abundance. It could persist quietly, patiently on the edge of existence, single cells feeding on minerals drifting through the eternal dark. That is Europa's paradox, a frozen world powered by warmth, a lifeless surface hiding conditions familiar to our own beginnings. If life arose once on Earth in the boiling shadows of deep-sea vents, perhaps it could rise again here, not beneath sunlight but beneath ice. The heart of Europa does not beat with fire but with movement. And in that movement, a question echoes through the dark: if warmth can find its way into this frozen sea, what else might awaken with it? There are places in the cosmos where sunlight never reaches, places that defy our idea of what life needs. Europa is one of them. Here, under kilometers of ice, life, if it exists, cannot rely on the gentle warmth of a dawn or the nourishment of a ray of light. Instead, it must live on something older, quieter, and far more fundamental: chemistry itself. On Earth, we call it chemosynthesis, the art of feeding on the imbalance between molecules. It is life drawn from reaction, not radiation. Wherever chemicals meet in disequilibrium, energy flows and organisms have learned to harvest it. Deep below our oceans, bacteria do this by using hydrogen, sulfur ion, or methane invisible currencies that buy survival in the dark. It is the same principle that might govern the unseen ocean of Europa. At Europa's seafloor, hydrogen bubbles from rock as it reacts with water in the process of serpentinization. Carbon dioxide dissolves into that water, carried downward from the crust. The meeting of the two produces energy, the kind that can fuel metabolism. Bacteria on Earth use this very reaction, combining hydrogen and carbon dioxide through chemical pathways that build sugars and organic molecules. No sunlight, no photosynthesis, only chemistry feeding chemistry. Imagine a world where life survives not by hunting or photosynthesis, but by balance, where organisms anchor themselves to rocks, absorbing the flow of electrons that drift between minerals. Tiny filaments of bacteria might bridge the gradients like living circuits, transferring energy the way trees on Earth share sugars through roots. Each cell a small battery, each colony a slow-breathing network of reaction and renewal. In Europa's ocean, these microbes would not grow fast. They would be patient, cautious, conserving every joule of energy. Their metabolism might be thousands of times slower than ours, but speed does not define life, endurance does. If such microbes exist, they could persist for eons, thriving in silence beneath the ice, unseen and undisturbed. Scientists model these possibilities not as fantasy but as probability. The math is simple. If the ocean has water, carbon, hydrogen, and minerals, then disequilibrium must exist. And where disequilibrium persists, energy is waiting to be used. Life at its core is the universe's most efficient way of restoring balance, of letting reactions happen through organized forms. It's chemistry given direction, intention, and memory. Europa's ocean could be filled with that quiet intelligence of chemistry. Hydrogen streaming from rocks, oxidants like oxygen and hydrogen peroxide, filtering down from the irradiated surface, both sides of a natural battery connected by an ocean-wide circuit. The crust of Europa might serve as the membrane separating the oxidizing and reducing layers. Every time that chemical tension relaxes, energy is released enough, perhaps, to keep microbial metabolisms alive. Consider the flow. Above Jupiter's radiation splits water molecules on the surface, creating oxidants like O2 and H2O2. Over time, these drift downward, embedded in the ice, carried slowly to the ocean below. Below, the seafloor releases hydrogen and reduced minerals upward. When the two meet, they react a perfect energy cycle powered by physics and patience. No star required, no seasons, no storms, only the constant hum of chemistry like an eternal tide. If we could stand beside one of those hydrothermal vents and watch this invisible dance, we would see no flame, no color, only the shimmer of molecules moving from high energy to low, the endless cascade toward equilibrium. And yet in that descent lies all creation. From the simplest gradients, complexity blooms. Carbon binds with hydrogen, nitrogen with oxygen, forming chains, rings, membrane structures that can grow, divide, remember. It is the alchemy of life written in its most minimalist form. Even without light, ecosystems could arise. Microbes feeding on hydrogen and sulfur, others consuming their waste, forming an unbroken web of energy recycling through darkness. Perhaps strange creatures, translucent eyeless, drift slowly above, sensing warmth instead of light, pressure instead of sound. Perhaps none of them exist yet, but the chemistry waits ready. Europa's ocean may not sparkle, but it moves, breathes, and reacts. And that is enough for life to try. If the universe has shown us anything, it is that life is opportunistic. Wherever there is an imbalance, it will find a foothold. Wherever there is energy, it will build a pattern. On Europa, that pattern may be hidden beneath miles of ice, slow, silent, and ancient, but it would obey the same rule written across the cosmos. Light creates life where it shines. Chemistry creates life where it can. And in Europa's darkness, chemistry shines brighter than any star. Beneath Europa's ice, there is no sky, no moonlight, no rhythm of day and night, only the steady pulse of gravity and heat. Yet even in this eternal dark, the ocean might be far from lifeless. It could host a slow, hidden ecology, where every movement and reaction serves a purpose honed by billions of years in isolation. Imagine entering that ocean. The descent begins in silence, a dim blue light filtering through ice that glows faintly with Jupiter's reflection. As you sink deeper, that light fades into grey, then into black. Pressure mounts, crushing down with thousands of atmospheres of weight. Still, the water does not freeze. It moves stirred by tides that rise and fall, invisibly driven by Jupiter's pull. At the bottom, you reach a world sculpted by warmth. The rocky floor breathes in slow eruptions of heat, and minerals shaping chimneys of frozen salt and metal. Around them, faint clouds of hydrogen and sulfur drift upward, feeding invisible colonies. There are no plants, no photosynthesis, only the quiet efficiency of chemosynthetic life, converting energy from the planet's heart into growth. Scientists on Earth study analogues in our own oceans, hydrothermal vent ecosystems that survive without sunlight. Their microbes capture chemical energy, forming the foundation for entire communities. Tube worms stretch like pale ribbons, shrimp crowd near plumes of heat, and strange fish hover in the shadows. Each creature depends on the chemistry rising from the crust. If Europa's vents work the same way, then its ocean could harbour similar if slower hierarchies of life. But what would evolution look like in such a place? Without light, eyes may never evolve, or they may fade away entirely. Instead, life might rely on pressure, vibration, and electric fields. Perhaps some organisms sense the faint electromagnetic hum of the vents, an ocean alive with silent frequencies. Perhaps they communicate through changes in current or by releasing pulses of ions through water thick with salt. Sound itself could be different here, muffled lower, a deep resonance that carries emotion instead of tone. In the shallower layers nearer to the underside of the ice, another world might exist. Their chemical oxidants, oxygen peroxide nitrates, descend from above, frozen into crystals that drift like snow. As they melt, they feed microorganisms clinging to the ice ceiling. Imagine vast microbial mats stretching across the inner surface of the ice shell, glowing faintly as they metabolize the oxidants from the frozen crust. These mats could be the forests of Europa, not green, not luminous, but persistent. Each square meter a fragile ecosystem, a slow exchange of nutrients between the surface and the sea below. Energy would be sparse, so growth would be patient. A single microbe might divide only once every few years or even decades. But in cosmic terms, time is generous. What takes millennia for us could be a blink for Europa. Life here would not rush, it would endure. Evolution in the dark might produce creatures adapted not for speed, but for awareness. Slow swimmers shaped like ribbons could glide by sensing gradients in heat. Some might carry internal chemical sensors, able to detect distant vent plumes the way a shark on Earth smells blood. Others could use faint electric discharges to map their surroundings, a natural sonar made of voltage. And in this deep stillness, predators might exist too, guided not by sight, but by the tremor of a fin or the brush of a current. Perhaps entire food chains drift upward from the vents, microbes consumed by larger grazers, which in turn fall prey to silent hunters that prowl through chemical twilight. No color, no sound, only movement. A ballet of adaptation written in darkness. And yet such an ecosystem might be fragile beyond imagination. If the tidal heat ever lessened or the chemical flow slowed, the entire network could collapse. That is the beauty and the terror of Europa's potential biology. A living system balanced on the narrowest margin between freezing and flowing, between energy and stillness. Still, there is resilience in that fragility. Even if no complex organisms swim there now, the potential for them exists. Given enough time, and Europa has had plenty, the chemistry of survival may sculpt forms as strange and elegant as anything we could dream. Life, after all, is a sculptor with infinite patience. It does not rush. It adapts, waits, and endures. So when we look up at that tiny point of light orbiting Jupiter, we are not just seeing a moon of ice. We may be seeing a mirror, a reflection of how the universe breathes life into darkness. Europa's oceans, silent and unseen, could be the most ancient story, retold that even in the coldest corners of space, nature cannot resist creating something that lives. Every living world, even a hypothetical one, must obey limits. Europa's ocean, for all its grandeur and possibility, would be no exception. Its life, if it exists, must find a way to balance within boundaries drawn by chemistry, temperature, and time. The deeper we understand those limits, the more clearly we see how fragile and how remarkable such a system might be. First, the challenge of energy. The tidal heating that stirs Europa's heart is not infinite. It fluctuates as the moon's orbit changes over millennia. When Europa drifts closer to Jupiter, its crust flexes more violently, producing bursts of heat and tectonic stress. When it drifts away, the heating subsides, the crust stiffens, and the vents may fall silent. If the balance shifts too far, the deep ocean could freeze from the top down or boil from the bottom up. Life here must endure these cycles, centuries of abundance followed by epochs of scarcity. Then, the challenge of nutrients. Unlike Earth, Europa has no rivers to wash minerals into the sea, no atmosphere to deliver carbon from the sky. Everything that sustains its ocean must come from two sources: the seafloor below venting minerals upward, and the surface above where radiation creates oxidants that trickle downward through cracks in the ice. Between these two extremes lies a vast dark water column, kilometers thick, where mixing happens only slowly. Scientists estimate that it might take millions of years for a molecule from the surface to reach the bottom. In such a world, nutrients are precious and slow to circulate. Every atom of carbon, sulfur, or nitrogen would be used and reused countless times before it vanished into mineral silence. And yet resilience may bloom in this scarcity. Life on Earth's most extreme frontiers has already shown that simplicity can outlast abundance. Microbes in our own deep biosphere, buried kilometers beneath rock, survive on traces of hydrogen and radiolysis products, dividing perhaps once per century. Europa's organisms, if they exist, could be similar, metabolically minimal, yet astonishingly durable. In that deep ocean, survival would not mean thriving. It would mean persistence, maintaining just enough energy to repair, to replicate, to continue. Pressure too shapes possibility. At the base of Europa's ocean, the weight of water is enormous, more than 1,000 times greater than the pressure at Earth's surface. protein cell membranes and molecules would need to evolve extreme stability. But nature has done this before. In our deepest trenches, earthly microbes endure the same crushing force. Their enzymes adapted to pressure that would destroy anything from the surface. They prove that life can shape itself to any gravity, any weight, so long as it finds chemistry that works. So Europa may host not thriving abundance, but quiet endurance. A world of slow metabolisms and patient cycles life that persists, even when energy falters. It is a sobering thought and a hopeful one. For if something can endure there in the coldest, darkest sea in the solar system, then life's strength is not in its brilliance, but in its refusal to stop. If Europa's ocean truly lives with warmth below and chemistry in motion, then it must also breathe. Every system that stirs eventually exhales, and perhaps Europa's breath escapes not through its seafloor, but through the cracks that lace its frozen shell. Scientists believe that in certain moments, tidal stress pulls those fractures apart, opening slender corridors that reach down toward the hidden sea. Through these channels, vapor salt and microscopic ice grains may surge upward, carrying with them the fingerprints of the deep. For a few hours, the ocean might touch space. Then the cracks close again, sealing the secret world beneath a mirror of ice. When the Hubble Space Telescope turned its gaze toward Europa, it caught a faint shimmer columns of vapor rising hundreds of kilometers above the surface, only to vanish into the vacuum. It was as if the moon had whispered exhaling proof of its inner life. These geysers are not constant. They appear and fade, timed with Europa's orbit synchronized with Jupiter's pull. Each eruption could be a pulse, a heartbeat, a release of pressure from the ocean below. For planetary scientists, these plumes are the bridge they've been waiting for. If we cannot yet dive beneath the ice, perhaps we can sample what escapes through it. Each grain of frozen spray, each molecule of vapor, might carry a story, the chemistry of salt carbon, or even the faint trace of something biological. So the search for life no longer begins at the seafloor. It begins at the cracks. Europa breathes, and in that breath we may find its truth, a direct line between a hidden ocean and the open void between silence and discovery. For decades, Europa was silent, a distant glimmer orbiting Jupiter, wrapped in ice, yielding no movement but what physics required. Then in 2012, that silence cracked. From more than 600 million kilometers away, a telescope orbiting Earth saw something no one expected: Europa breathing. The Hubble Space Telescope, equipped with its ultraviolet spectrograph, was not designed to see worlds like this. It was built to study galaxies, nebulae, and dying stars. Yet when scientists turned it toward Europa's limb, they found a faint glow extending above the horizon, ghostly and blue. At first they thought it was noise, an artifact of the instrument, but the pattern was too precise, too symmetrical, rising exactly from the same longitude, fading as Europa moved through Jupiter's magnetic shadow. Something real was happening. The analysis revealed the signature of water vapor. Europa was venting plumes hundreds of kilometers into space geysers, erupting through its frozen shell. Not constant, but episodic, like sighs from a sleeping ocean. Each plume released thousands of kilograms of vapor, enough to coat the surface in frost, yet so subtle it was invisible to the naked eye. The implications were immediate and breathtaking. For the first time, there was direct evidence that Europa's surface connects to its hidden ocean. If these geysers truly originate from below, then they offer a shortcut, a way to study the subsurface sea without ever drilling through the ice. Every particle in those plumes is a messenger from the abyss. To confirm it, Hubble observed again 2014, 2016, 2018. Sometimes the plumes appeared, sometimes they didn't. That inconsistency only deepened the mystery. Why would they flare and vanish? Why only at certain points in Europa's orbit? Models soon revealed a rhythm: the plumes are strongest when Europa is farthest from Jupiter. At that moment, tidal forces stretch the moon to its limits, widening cracks across the southern hemisphere. Water vapor escapes through those fractures, freezing instantly as it meets the void. Then, as Europa swings closer, the stress reverses the fissures close, and the geysers fall silent. It is as if the moon breathes in and out once every orbit, its inhale measured in gravity, its exhale in vapor. The detection electrified the scientific community. Suddenly, what had been theory, the idea of a subsurface ocean communicating with space, became tangible. Hubble's ultraviolet glow was faint, yet its meaning was profound. Europa was active, alive in a geological sense. The world once thought static was now dynamic, unpredictable, alive with energy. For the engineers designing the next generation of spacecraft, this discovery changed everything. If plumes truly exist, a probe could fly through them, collecting frozen spray without landing or drilling. It could sample Europa's ocean directly, its salts, organics, and maybe even cellular debris all suspended in those drifting crystals. The thought was almost impossible to believe life from another world delivered to us on a stream of vapor, but as with all discoveries, Hubble's finding raised as many questions as it answered. Were the plumes fed by shallow reservoirs of meltwater, or did they reach all the way to the ocean below? How often do they erupt? Are they triggered by tides, heat pockets, or chemistry at the base of the crust? Each possibility carried a different vision of Europa's interior, a world of slow, stable motion, or of restless, shifting ice. And so what began as a faint ultraviolet glow became the most compelling invitation in planetary science. Europa was no longer just a question of geology, it was a question of access. Somewhere beneath its frozen skin, an ocean stirs, and now, through those transient plumes, it might be whispering to us across the void, a message written not in language but in vapor and light. For a long time we'd watched Europa and wondered what secrets it hid. Then for the first time it spoke not loudly but softly in a single exhale of steam that travelled 500 million kilometers to reach the eyes of a telescope orbiting Earth. A whisper from a buried sea finally heard. Long before Hubble caught Europa in the act of breathing, another witness had already passed through the mist, though no one realised it at the time. It was 1997 and NASA's Galileo spacecraft was deep into its mission around Jupiter. The probe had already survived 1,000 radiation storms, 1,000 encounters with the giant's magnetic wrath. But during one of its closest flybys of Europa, something unexpected stirred in its data, a faint disturbance, a whisper of plasma and magnetism that made little sense. At first, scientists thought it was just noise, a blip caused by Jupiter's electric fury. But years later, when Hubble discovered those vapor plumes rising from Europa's south pole, someone went back to Galileo's archives. They re-examined that strange signal from December 16, 1997, and everything changed. The spacecraft had flown within 200 kilometers of Europa's surface. Its instruments recorded a sudden spike in charged particles, a fluctuation in magnetic field strength, and a brief deflection in its plasma wave data. The kind of response you would expect if the probe had flown through a cloud of ionized water vapor. For 20 years, those numbers had slept in the data vaults unexplained, overlooked. But when the Hubble findings came to light, they snapped into focus like a forgotten photograph restored to clarity. Galileo had not just passed near Europa, it had flown straight through one of its plumes. To confirm it, researchers at the University of Michigan built a detailed model of Galileo's trajectory and Europa's magnetic environment. The results matched perfectly the spacecraft's instruments, behaved exactly as they would if they were engulfed in a stream of water vapor venting from the moon's surface. The density, the ion composition, the magnetic disturbance all aligned with a passing through a plume roughly 1,000 kilometers long and 200 wide. In hindsight, it was as if Europa had reached out for a moment, brushing against the first machine ever to orbit its parent world. The contact had been silent, invisible, and unnoticed, a handshake across time. That revelation turned Galileo's old data into something sacred, a record of direct contact between Earth and a possible alien ocean. Every sensor tick, every voltage shift, every magnetic twitch became a clue. From those faint traces, scientists could estimate the mass of the plume, the speed of its particles, even the potential composition of the water. The results were astonishing. The plume was composed primarily of water vapor mixed with traces of sodium chlorine and possibly organic molecules. In other words, ocean chemistry. Not exotic compounds from the solar wind, not frost sublimating from the surface, but genuine salty water from within. Europa had given us a sample before we even knew to ask. That flyby also changed how missions are planned. NASA engineers realized that if a spacecraft could pass through one of these plumes again intentionally, this time it could literally taste Europa's interior without ever landing. No drilling through kilometers of ice, no risk of contamination, no waiting for robotic submarines. Just a simple, swift crossing through vapor and dust, collecting what the moon willingly offers to the void. The thought still feels miraculous that across 500 million kilometers of space, a moon might send its ocean skyward where we can reach it. That every particle drifting from those geysers might carry within it the memory of a world below its chemistry, its history, perhaps even its biology. And yet, as with every revelation, doubt remains. Could those signals have come from something else, a localized magnetic anomaly, or a temporary burst of charged plasma from Jupiter's field? Science thrives on skepticism, and Europa is generous with uncertainty. But even the most cautious voices agree if Galileo's data are not proof, they are an invitation, one that no future mission can ignore. Today, when scientists replay that 1997 flyby, they listen differently. In the static of a decades-old transmission, they hear the echo of the moment humanity unknowingly touched an alien world. The instruments were crude by today's standards, the analysis rough, but the evidence endures a line of numbers whispering across time: we were here and it reached for us. The next generation of explorers will return equipped with sharper tools and wiser eyes. They will not just pass through the vapor, they will read it, taste it, understand it. And when they do, Galileo's forgotten moment will become the prologue to discovery, the first accidental breath in a dialogue that continues still between our curiosity and a moon that breathes. Europa's plumes are more than spectacles, they are doorways. They are the first natural bridges ever seen between an alien ocean and the vacuum of space. Each eruption, each ghostly exhale is a channel that connects two impossible worlds, one of crushing pressure and liquid darkness, and one of silence, radiation, and endless night. And through those channels, for a fleeting instant, the ocean below touches the stars. Scientists now see the plumes as the key to understanding everything hidden beneath Europa's icy armor. They rise not as random bursts, but as rhythmic responses to gravity, temperature, and chemistry. When Jupiter's tides flex, the moon cracks stretch and narrow, opening thin paths that can reach kilometers into the ice shell. Underneath, pockets of liquid water, perhaps shallow lakes or direct extensions of the global ocean, are pressurized by that flexing. When the stress peaks, they erupt. Vapor jets through the fissures, flinging ice grains and salt crystals into the sky. Then, as the pull relaxes, the cracks freeze again, sealing the cycle until the next orbital breath. Each plume is both fragile and ferocious. The gas accelerates at hundreds of meters per second, forming towering jets that can rise hundreds of kilometers before falling back as frozen snow. Most of the material never escapes, it rains down again, coating Europa's surface with fresh frost. But some of it drifts into space, joining the faint ring of particles that orbits Jupiter, proof of Europa's slow, steady exhalation. To planetary scientists, this process is nothing short of miraculous. Until now, every attempt to study an extraterrestrial ocean has been limited by distance and depth, a surface too thick to penetrate, an abyss too far to reach. Europa's plumes solve that. They are nature's own sample return system, carrying traces of the interior into space, waiting for us to collect them. Models of Europa's internal structure suggest that these plumes could originate from several sources. Some may emerge from shallow reservoirs, melt zones where heat from below softens the ice. Others might be rooted in deep fractures that pierce all the way to the ocean itself, delivering water from kilometers below. If that second possibility is true, then each plume contains unfiltered material from a place where life could exist. A single grain of ice, a single molecule of salt could hold a record of Europa's chemistry, its oxygen, its carbon, its history of motion and renewal. NASA's upcoming Europa Clipper and ESA's JWST missions are designed to investigate precisely this. Their spectrometers, dust analyzers, and plasma sensors will be tuned to detect molecules within these plumes, salts, carbon compounds, amino acids, or complex organics. If the spacecraft can fly through a jet just once at the right time, it will be able to taste the moon's ocean without breaking the ice at all. A single pass could reveal more about Europa's interior than decades of theory. But these plumes are not constant. They're elusive, unpredictable. Sometimes Hubble sees them, sometimes it doesn't. They appear strongest when Europa is farthest from Jupiter, a clue that their origin is tied to the tides, to the stretching and relaxing of the crust. That makes planning a flyby a delicate ballet. Each spacecraft must arrive during the moon's orbital exhale, when the fractures yawn open just long enough to vent their secrets. Beyond the mechanics lies a deeper question. What drives the pressure that powers them? Tidal stress is part of the answer, but chemistry may play a role as well. When salty water freezes, it releases trapped gases. When minerals react with oxidants from above, they create additional volatiles, oxygen, hydrogen, carbon dioxide that can build up in sealed cavities. Given enough tension, those cavities can explode, shooting vapor into the vacuum like geysers on command. And so Europa's surface becomes a breathing interface. Its cracks the lungs of a hidden sea. Each plume could be the endpoint of a planetary metabolism, a slow exchange between the warm rock below and the frozen crust above. It is a system that mimics biology at a planetary scale, energy building, pressure releasing, balance restored. From an engineering perspective, plumes are a gift. They make Europa not a fortress, but an invitation. No other ocean world in our solar system offers such direct access to its depths. Enceladus, Saturn's smaller moon, also vents geysers, but Europa's are grander, older, and potentially richer in chemistry. If one of those plumes contains even the faintest trace of organic material, it will mean that the ocean below is not sterile. It is active, reactive, possibly fertile. Imagine that moment a spacecraft glides through a column of frozen breath, its instruments whirring softly, collecting particles no larger than dust. Each grain of ice carries a story from beneath the crust, perhaps of salt and mineral, perhaps of amino acids clinging to crystals, perhaps of something more. A few milliseconds of passage and the data is stored, traveling back across hundreds of millions of kilometers to Earth. Within those numbers, the first hint of alien chemistry may be waiting. The plumes of Europa are in every sense thresholds. They are gates between what we can see and what we can only imagine. They blur the line between the known and the possible, between the surface and the abyss. Through them, the ocean speaks not in words or symbols, but in the quiet rhythm of pressure and release. If the story of Europa is a song, then the plumes are its chorus, a reminder that even in the frozen silence of the outer solar system, something is still breathing, still moving, still daring to reach outward into the dark. When the next spacecraft reaches Europa, it will not look for seas or mountains. It will look for dust. Tiny particles no larger than grains of sand drifting in arcs of frost around the moon may carry answers to one of the oldest questions ever asked. Are we alone? Those grains are the messengers of the ocean below. They form when vapor erupts from Europa's plumes and freezes instantly in the vacuum of space. Each one is a capsule trapping within it a drop of seawater, a perfect record of its birthplace. Some may contain nothing more than salts and ice. Others could hold carbon compounds or even molecular relics of biology, amino acids, lipids, or fragments of complex polymers formed in the dark. To find life on Europa, we must learn to read these frozen letters drifting in the void. The task is daunting. At the speed of an orbital flyby, a spacecraft will cross a plume in seconds, just a blink in cosmic time. Yet those seconds can yield miracles if the instruments are ready. The Europa Clipper mission launching soon carries tools designed for exactly this kind of hunt. Among them are MassSpecs, the mass spectrometer for planetary exploration, and SUDA, the surface dust analyzer. Together they form humanity's first true taste buds for another world. MassSpecs will capture vapor and analyze it molecule by molecule, breaking each into fragments, identifying their masses with exquisite precision. If methane, ammonia, or simple hydrocarbons appear, it will tell us. If amino acids or long carbon chains are present, it will know. It can even detect isotopic ratios, subtle fingerprints that can distinguish chemistry shaped by life from chemistry shaped by chance. SUDA, meanwhile, will collect solid particles, the icy grains that drift outward from Europa's geysers. As they strike its detector plate at thousands of kilometers per hour, the grains will vaporize into plasma. That plasma in turn becomes a spectrum, a burst of light, and ions decoded into elements and compounds. In each flash, the moon's ocean speaks. But interpreting those signals will not be simple. The signatures of life and the signatures of geology can look eerily similar. Amino acids can form abiotically. Methane can emerge from rock. Organics can mimic biology in every way except intention. To call something alive, we must see more than molecules, we must see patterns. Life arranges matter into a symmetry, left-handed amino acids, specific carbon chains, recurring ratios that favor order over randomness. It leaves behind organization even in chaos. That is what these instruments will search for, not proof, but pattern. The beauty of this method lies in its gentleness. We do not have to drill or disturb Europa's crust. We only have to listen to what it offers. Each plume becomes an open laboratory, each dust grain a self-contained experiment. We are not invaders, we are witnesses. Still, there are challenges. The radiation around Jupiter is fierce, capable of breaking molecules apart faster than instruments can read them. The plumes themselves may be inconsistent, appearing only during certain orbital alignments, and the quantities involved are infinitesimal, a handful of ice crystals among billions. Yet humanity has learned to hear whispers before. We have detected the vibration of atoms from galaxies billions of light years away. We have measured the decay of particles that last less than a heartbeat. To listen for the chemistry of life on Europa is simply the next verse in that long, patient song of curiosity. Imagine the moment of detection. The spacecraft crosses the plume at breathtaking speed. The data pours in spikes of oxygen, carbon, nitrogen, sulfur. A pattern emerges, perhaps a complex molecule, perhaps a ratio too precise to be random. Scientists back on Earth wait as algorithms translate the signals into spectra and the spectra into meaning. Then for the first time, the chemical rhythm of an alien ocean appears on a screen, familiar yet foreign. The room falls silent. Whether that pattern turns out to be biology or not almost doesn't matter. In that instant, we will have touched the ocean of another world, not with our hands, but with our instruments, our patience and our faith in the power of questions. Each molecule found there will stretch our understanding of what it means to be alive. Perhaps the ocean holds cells and metabolism. Perhaps it holds only potential chemistry poised forever on the edge of becoming. Either way, we will have found something extraordinary, the bridge between the physical and the possible. For in every grain of ice that leaves Europa, there is a story written in salt and carbon. We only have to learn to read it. And when we do, we may find that the line between chemistry and life, between motion and meaning, is thinner than we ever imagined. The hunt for life on Europa is not a pursuit of spectacle. It is a pursuit of traces of invisible threads linking matter to memory, chemistry to intention. Every vapor jet, every grain of frost, every spark in a detector is a letter from the deep written in an alphabet we're only beginning to learn. Through the plumes, Europa has given us access to what was once unreachable. No longer must we dream of drilling through miles of ice or sending submarines into a sea of darkness. The ocean comes to us molecule by molecule, frozen into dust, drifting like breath into the void. And with it comes the first chance in human history to test a hypothesis as old as wonder itself. Can life emerge wherever energy meets water, even without the light of a star? This question is no longer theoretical. We now hold the tools, the timing and the technology to answer it. The Europa Clipper will measure the vapor, JWST will scan the crust. Together they will search not for aliens, but for chemistry behaving like life. Patterns of carbon, nitrogen and oxygen. Isotopic ratios tilted away from randomness. Molecular chains too deliberate to be coincidence. For centuries humans have looked outward and wondered if the stars might host other worlds like ours. Now we look not to the stars but to the ice, and find that alien oceans may have always been within our reach. When the next plume erupts and a spacecraft glides through it, every droplet it catches will be a message carried across billions of years, a whisper from a world that remembers what heat feels like in the cold. From here onward, the search deepens from vapor to molecule, from chemistry to the very architecture of life itself. From a distance, Europa gleams like glass, a perfect pearl orbiting within Jupiter's electric crown. But when you draw closer, the illusion fractures. The moon's face is not pure white. Across the plains of ice stretch stains of rust amber, and deep maroon thin veins and patches that cut through the brilliance like ancient scars. In the telescope's eye, these colors pulse with quiet complexity, hinting at the story written just below the frost. For years, planetary scientists puzzled over this palette. Why should a world of frozen water shimmer with tones of blood and bronze? The answer, it turns out, is chemistry, a dialogue between radiation, salt and time. Jupiter's immense magnetic field wraps around Europa like a storm of invisible lightning. Charged particles bombard the surface at near-light speeds, splitting water molecules apart, tearing oxygen from hydrogen, rearranging everything they touch. What was once clear becomes painted with new compounds: sulfur dioxide, hydrogen, peroxide, magnesium, sulfate, and a dozen other oxidized fragments. They fuse with salts dragged upward from the ocean below, forming a skin of red and brown minerals baked by radiation. Each color is a clue. The yellow streaks that wind across Europa's equator may come from sulfur carried on magnetic lines from the nearby moon, Io Jupiter's volcanic furnace. The darker, more ochre tones appear where the ice has fractured recently, suggesting something rising from beneath briny material pushed upward through pressure freezing mid-eruption. In those regions, the surface looks bruised, as if the moon itself is healing from its own geology. Spectral data from Galileo and JWST reveal signatures consistent with sodium chloride, simple table salt mixed with compounds altered by radiation. Under Earth-like light, that salt would look white. Under Jupiter's relentless bombardment, it burns red. To a scientist, these colors speak of chemistry in motion. To a storyteller, they whisper of communication, a way for an ocean to announce its presence without breaking the ice. Every rust-coloured ridge could be a place where water once touched the surface, evaporated into space and left its memory behind. Every amber band is a postcard from the abyss. Europa's hues also change with time. Freshly resurfaced plains gleam bluish-white, while older terrains darken as radiation cooks their chemistry. The moon is repainting itself, continually erasing the ancient with each tidal cycle. This constant renewal explains why Europa's face bears so few impact craters. The skin is young, the canvas endlessly rewritten by internal motion. Where we see brown and gold, we are witnessing evidence of renewal, proof that the moon is active, not frozen in geologic death. And beneath those stains lies carbon, perhaps the most telling colour of all. Recent observations from the James Webb Space Telescope revealed concentrated patches of carbon dioxide along chaotic regions, tangled mosaics of broken ice that appear to have melted and refrozen many times. Carbon, like hydrogen and oxygen, is a universal player in the chemistry of life. Its presence on Europa's surface is not just aesthetic, it is existential. It implies that carbon from the ocean below is making its way upward, carried by convection, trapped in the cracks and frozen into the light. When sunlight hits those spots, pale but persistent sunlight from 1 billion kilometers away, it reflects differently, scattering into red wavelengths that our instruments capture as color. In that faint reflection is an ancient pattern, energy meeting matter, forming complexity. A process we recognize because we have seen it before in our own world, in our rocks, in our blood. So the next time you see an image of Europa, notice the imperfections. The brown fractures, the copper streaks, the subtle reds around its equator. They are not flaws, they are signatures. The fingerprints of radiation and salt of chemistry, alive and restless beneath the ice. Europa's surface, painted by storms and tides, is more than a shell, it is a language. And every mark, every colour is a syllable in the ocean's long, slow attempt to be understood. The James Webb Space Telescope peers across 500 million kilometres of emptiness, its golden mirrors tuned to light too faint for any human eye. And in 2023, when it turned toward Europa, it saw something extraordinary. Not motion, not reflection, but a chemical whisper, carbon dioxide gleaming faintly along the fractured plains of chaos terrain. For decades we suspected that Europa contained carbon. After all, carbon is the alphabet of life, the framework upon which every molecule of meaning is built. But proving its presence on a distant icy moon was nearly impossible. Earlier telescopes had caught glimpses, low-resolution hints, fleeting signals drowned by noise. It was like hearing a single note in a storm and trying to name the song. But JWST changed that. With its infrared spectrometer sensitive enough to detect the faintest bonds between atoms, it mapped Europa's surface with unmatched clarity. What it found was not uniform. Carbon dioxide was not scattered randomly across the ice. It was concentrated in specific regions, the chaos terrains where the crust appears shattered, melted and refrozen as if the moon's skin had boiled from within. These regions are younger, fresher, more dynamic than the rest. They are also the most likely places where the ocean below has touched the surface, either through upwelling cracking or cryovolcanic eruptions. And there, in those tangled fields of frozen turmoil, JWST detected the unmistakable spectral fingerprint of CO2. This discovery changed the conversation. It meant that carbon, once thought to be delivered only by comets or micrometeorites, was actually coming from inside Europa itself. Something within that ocean was supplying the surface with carbon-bearing material. And if that is true, it rewrites our understanding of Europa's chemistry entirely. Carbon dioxide on a world like this can't survive long on the surface. Jupiter's radiation would strip it away in a matter of thousands of years, a blink in geological time. So the fact that it is there visible now means it must be constantly replenished. Something below the ice is generating it, sending it upward through fissures and vents to freeze into the crust before radiation tears it apart again. It is an ongoing cycle, an exchange between the interior and the void. To scientists, that cycle is more than chemistry. It's proof of communication. The surface and the ocean are not isolated. They are in dialogue. Material moves up, freezes, erodes and returns. Energy moves down, melts, stirs and renews. This circulation is exactly what life in its most basic form requires, a bridge between stability and change, between chaos and order. Some of the carbon may form through abiotic reactions, simple chemistry at the seafloor where rock meets water. When carbonates dissolve or methane oxidizes under heat, carbon dioxide emerges naturally. But on Earth, Similar reactions coexist with biology. At hydrothermal vents, microbes feed on carbon dioxide, turning it into organic compounds, only for those compounds to decay and release CO2 once again. It's a loop of metabolism that binds chemistry and life in the same breath. Could Europa's ocean operate the same way even without sunlight? The possibility lingers unprovable, yet irresistible. The pattern on the surface is telling the strongest CO2 signal appears near Terra Regio, a vast region of chaotic terrain believed to have formed through partial melting of the crust. The ice there has been turned over renewed from below. If the carbon dioxide there truly originates from the ocean, it means that the chemistry of the deep is still rising, that Europa's heart is still speaking through the fractures of its frozen face. In that sense, the chaos terrains are not scars, they are lungs. They exhale the products of deep processes, gases, salts and minerals into the thin exosphere, where telescopes can finally catch their breath. And the fact that JWST could see that signal at all from across the solar system tells us that Europa's exhalations are not faint. They are steady, persistent, alive with chemistry. There is poetry in this, the most advanced telescope ever built, using infrared light to study the faint heat signatures of distant galaxies, now turning inward to find signs of possibility on a moon orbiting our own giant neighbour. It reminds us that exploration is not always about distance, but about depth, about listening more closely, not just looking farther. When JWST detected carbon dioxide on Europa, it did not prove life, but it proved potential. It proved that the ingredients for life are not just theoretical, they are active, mobile cycling through a world we once dismissed as frozen. Europa is not a dead relic. It is a restless machine of chemistry humming beneath ice, and somewhere below that chaotic crust, carbon still moves dissolving, combining, transforming, waiting for the next crack to open, the next plume to rise, the next instrument to listen. The brown and red stains we see from afar are not stains at all. They are the signatures of persistence, proof that the ocean below is not silent. It breathes through chaos. It speaks through colour. And now through the eye of JWST we are finally beginning to understand its language. If carbon is the storyteller of the cosmos, then on Europa it may be writing in whispers, brief traces frozen into salt and ice. The next step in understanding that language lies not in what is alive, but in what could be. Because before there is biology, there must be chemistry. The intricate patient architecture that life inherits and refines. Europa's ocean is rich in the raw ingredients for such chemistry. Its seafloor likely hosts the same reactions that on Earth feed entire ecosystems in perpetual night. Hydrogen seeps upward from serpentinizing rock. Carbon dioxide dissolves in the briny water. Sulfur and iron circulate as quiet catalysts. Where these ingredients meet, they spark reactions that assemble complex molecules, hydrocarbons, aldehydes, alcohols, each one a step toward organic life. These molecules do not require biology to exist. They are abiotic organics born from simple physics and persistent energy. In the presence of minerals like olivine and magnetite, carbon and hydrogen, joined to form methane, methanol and formaldehyde, building blocks of carbon chemistry that have appeared in meteorites, comets and interstellar clouds. Europa, with its water, minerals and heat, is perfectly equipped for this same cosmic alchemy. Imagine the process unfolding in the dark. At the seafloor, hydrothermal vents exhale warm fluids laced with dissolved minerals. As those fluids mix with colder water, temperature gradients drive chemical disequilibrium. Carbon dioxide meets hydrogen in the presence of catalytic metal surfaces, forming simple organics. Layer by layer, they coat the rocks, creating thin films, molecular foreshadowings of membranes. Some dissolve into the water, some sink back into the crust, some rise upward in microscopic plumes. Over eons, this slow chemistry could transform Europa's ocean into a reactive broth filled not with life, but with the promise of it. The next link in that chain is amino acids, the bricks from which proteins and therefore behavior are built. We know they can form in the absence of biology. Lightning in early Earth's atmosphere produced them. Meteorites carry them freely through the solar system. Even in deep space, ultraviolet radiation acting on frozen ices can craft them. If that same radiation bombards Europa's surface, and we know it does, it could drive similar processes. Compounds created in the upper ice might migrate downward, mingling with the upwelling chemistry from below. The moon's surface then becomes both crucible and courier, transforming and delivering molecules between sky and sea. But Europa adds another twist. Because its surface is bombarded by Jupiter's radiation, It hosts a constant factory of oxidants molecules like hydrogen peroxide and oxygen that could trickle into the ocean. These oxidants, when mixed with reduced compounds from the seafloor, create an energy gradient, a perfect stage for complex reactions. If simple organics drift into that gradient, they might polymerize, forming chains, capable of storing energy or catalyzing new reactions. The chemistry would begin to organize itself, not yet life, but leaning toward it. The boundary between abiotic and biotic chemistry is thinner than we once thought. On Earth, certain minerals act as both scaffolds and catalysts for these transitions. Iron-sulfur clusters found in enzymes today have ancient geological analogues, natural catalysts that may have performed the same tasks before life existed. Europa's seafloor likely contains similar minerals. Its vents could therefore host reactions that mimic metabolism long before true biology ever arose. When scientists search Europa's plumes for organic molecules, they are not just hunting for life, they are looking for continuity. If the molecules detected follow certain ratios, if their isotopic weights or branching patterns suggest selective synthesis that would indicate processes edging toward biological complexity, if they appear random, evenly distributed, it would confirm a world still governed purely by chemistry. Both outcomes matter, because in either case, we would be seeing the architecture of life's foundation, and even if no living organisms swim in Europa's ocean, the discovery of abiotic organics alone would be revolutionary. It would show that the path toward life is not rare or miraculous, but natural, a chemical inevitability waiting for the right moment. It would tell us that the universe doesn't need divine accidents to create biology. It just needs time, water, and energy. Picture it a world of black water beneath unbroken ice molecules drifting for eons, occasionally colliding, bonding, breaking apart. Each reaction adds a new fragment to a cosmic sentence written in carbon. Most lead nowhere, but some, just a few, linger, self-reinforcing, repeating their structures, learning endurance. That persistence more than complexity is where life begins, and perhaps one day when a spacecraft skims through a plume and catches a grain of frozen salt, we will see not cells or organisms but molecules arranged in ways that seem almost deliberate, the chemistry of potential caught in mid-formation. The line between life and non-life, after all, is not a wall, it is a gradient, and Europa may exist right along that border, not alive, not dead, but becoming. To ask whether Europa hosts life is to ask something both simple and impossible. What does life look like when you've never seen it before? What counts as evidence when every molecule you find could be both artifact and accident? In this darkness, the word biosignature becomes not a declaration, but a discipline, a way to listen for patterns that only intention could write. Scientists define a biosignature as any measurable feature that cannot be easily explained by non-living chemistry. But that definition hides a labyrinth. On Earth, we have the luxury of context. We know how our biology shapes its chemistry. We know what life does to carbon, how it favors certain isotopes, how it builds molecules that twist to the left and never to the right. But on Europa, we stand without a frame of reference. Here, chemistry itself may perform tricks that mimic life's precision. So the real question becomes, how do we separate pattern from coincidence, order from the illusion of it? The answer lies in multiple lines of evidence signatures that overlap, reinforce, and resist randomness. No single molecule will be enough. Instead, scientists will look for convergence, several anomalies aligning into coherence. If Europa's ocean contains organic molecules, isotopic ratios and structures that each independently hint at biology, and all within the same environment, the probability tilts from chemistry towards something that remembers. The first measure is isotopic fractionation, the subtle difference between heavy and light atoms. On Earth, living organisms prefer lighter isotopes of carbon, nitrogen, and sulfur because they react more easily. This creates fingerprints in rocks and oceans, measurable differences that betray the presence of metabolism. If Europa's carbon dioxide or methane displays similar imbalances, say a depletion of carbon-13 or an enrichment of nitrogen-15, it could signal processes that favor energy efficiency, something nature rarely does without reason. The second measure is molecular chirality, handedness. Amino acids and sugars can exist in two mirror image forms, left and right. Non-living chemistry produces both equally, but life, for reasons still debated, chooses one and sticks with it. On Earth, all amino acids are left-handed. This consistency is so extreme that finding an environment dominated by one chirality is considered near definitive evidence of biological sorting. If Europa Clipper's instruments detect such asymmetry in organic grains, it would be the faintest echo of cellular selection. a whisper of preference in a universe of symmetry. The third measure is complexity with purpose. Abiotic processes can build simple chains, methane, ethane, formaldehyde, but they struggle to produce long, stable molecules with repeating patterns, structures like lipids or proteins that require stepwise organization. A single chain might form by chance, but thousands of near-identical ones that hints at a system copying itself. If we were to detect recurring molecular sequences in plume grains, specific ratios of carbon to hydrogen, repeating backbones or side groups, that would be a red flag for self-regulation, the chemical foundation of persistence. Then there is context. Life never acts alone, it reshapes its environment. On Earth, microbial mats alter the chemistry of surrounding water, shifting pH, reducing metals, concentrating elements. If Europa's ocean were alive, its chemistry would not be random, it would be sculpted. Scientists will look for co-location organic molecules appearing alongside redox gradients, salts or minerals that could sustain metabolism. Patterns like these tell us the story is not static, but ecological. Yet for every signal that hints at life, there are a dozen ways nature can mislead us. Methane can form without biology. Amino acids can emerge in ice under radiation. Isotopic fractionation can happen through purely chemical diffusion. The challenge then is not to prove life exists, but to prove it is the simplest explanation left. That humility defines modern astrobiology, a readiness to be wrong paired with the courage to ask again. Consider a scenario: a future probe flies through a plume and collects ice grains. Inside those grains, it detects complex organics with ratios skewed toward light isotopes and faint signs of chirality. On their own, none of these signals confirm life, but together in concert in pattern, they begin to tell a story of chemistry organizing itself, of molecules aligning toward stability of the ocean below, moving toward memory. It would not yet be proof, but it would be an invitation to believe that proof might exist. The line between life and chemistry is not drawn by complexity, it is drawn by consistency. Abiotic reactions happen once, maybe twice. Life repeats itself stubbornly, insistently, until its presence cannot be ignored. It leaves order where there should be none. So the ultimate biosignature is not a molecule or isotope, but repetition, the same structure appearing across different samples, different times, different cracks in the ice. A voice that doesn't stop speaking. Still, even with the perfect data, a final truth may remain elusive, because what we call life might not even resemble our own. Europa's organisms, if they exist, may not rely on carbon chains or cell membranes. They might use ammonia instead of water, sulfur instead of oxygen, or exist as networks of reactive films on mineral surfaces. They might not divide, they might only flow, and so we may find life's evidence only in its shadow, in the way it disrupts chemistry's natural silence. In that sense, searching for biosignatures on Europa is as much philosophy as science. We are not just asking, does it live, but how would we know if it did? It is a test not only of Europa's secrets, but of our own imagination. To define life, we must meet something that challenges our definition. Perhaps when the data finally arrives, when the graphs flatten into meaning and the spectra into language, we will find patterns that feel familiar, ratios that hum like metabolism, sequences that feel intentional, and perhaps we will hesitate, because in that moment we will realize the question has reversed. It is not Europa that must prove it is alive, it is we who must prove we can recognize life when it speaks in another chemistry. Science at its most intimate is not about discovery, it is about translation. Each signal from Europa, every spike of carbon, every skewed isotope, every fragment of ice, is a phrase written in a dialect older than biology itself. We do not yet know what it says, but the act of listening, of searching for coherence in the noise, already brings us closer to understanding. The next step is no longer theoretical. We have mapped the colors, traced the salts, and seen the vapor rise. Now humanity prepares to cross from observation to contact, to send machines that can hear what our telescopes can only glimpse. The Europa Clipper will orbit, dip low, and taste the moon's exhalations. JWST will follow, scanning the crust with radar and magnetometers, searching for the outlines of hidden oceans. Each instrument becomes a sense, a new ear, a new eye, a fingertip brushing the skin of another world. But behind every equation and sensor lies something deeply human, the need to turn chemistry into story data, into meaning. We do not search for life only to find it, we search to understand what it means that life can exist elsewhere. That water and energy, given enough patience, might always try to remember themselves. The molecules waiting beneath Europa's ice do not care if we find them. They have been reacting for eons, rewriting themselves in endless repetition. But if in one of those repetitions we find a pattern that mirrors our own, an echo of organization, a rhythm of persistence, then we will have learned something greater than biology. We will have learned that the universe, in its infinite coldness, still holds the instinct to create warmth. The next great voyage toward Europa will not be made by sail or by starlight, but by signal. Its name is Europa Clipper, a spacecraft designed not to land or to dig, but to listen. It will orbit Jupiter loop through its magnetic storms and skim Europa again and again, 50 times each pass, closer than the last until the moon begins to reveal itself. This mission is humanity's most deliberate attempt yet to answer a question we have been circling for decades. If Europa hides, an ocean, is that ocean alive? The design of Europa Clipper is both elegant and brutal, a machine built to endure radiation strong enough to kill a human in minutes. Its aluminum body is wrapped in shielding. Its instruments are tuned to precision finer than breath. Every sensor is a sense, sight, touch, taste for a world no human may ever stand upon. The heart of this spacecraft lies in its suite of 9 scientific instruments, each crafted to interrogate a different layer of Europa's mystery. Together they form a chorus, a distributed consciousness designed to reconstruct the unseen. The first of these is the Reason radar, the radar for Europa assessment and sounding ocean to near surface. It will pulse radio waves downward through miles of ice, listening for echoes that bounce from subsurface lakes or the great ocean below. Each reflection is a syllable in a language of density and depth. By mapping how those echoes shift, Reason will trace the thickness of the crust, identifying regions where the ice is thinnest, places where the ocean nearly touches the vacuum. Next comes the Europa Imaging System, EIS twin cameras, one wide, one narrow. They will photograph the moon's surface in stunning clarity, resolving details as small as half a meter. Every fracture, every ridge, every smooth plane will be documented, giving geologists a map not just of shape but of time, a story written in frozen motion. From these mosaics we will learn how the crust moves, how it breaks, how it heals. Each scar is a timestamp marking Europa's living skin. To understand its heart, the Clipper carries the Europa Thermal Emission Imaging System, ETHEMIS, designed to read heat where our eyes see none. Warmth betrays energy. Energy sustains chemistry. If active regions exist, geysers, fractures, or vents, ETHEMIS will see their faint thermal glow. Even a difference of a few degrees could mark a pathway between the ocean and the surface. But Europa is not just a surface. It is an interaction with Jupiter's gravity, its radiation, its magnetic field. The magnetometer ECM will measure the moon's magnetic response in exquisite detail, sensing how its hidden ocean conducts electricity as Jupiter's field sweeps past. The strength and timing of that response will tell us the ocean's depth, its salinity, perhaps even its layering. In a world we cannot yet see, magnetism becomes a form of touch. Then there is MASSPEX, the mass spectrometer for planetary exploration Europa, and SUDA, the surface dust analyzer. Together they form the taste buds of the mission. MASSPEX will inhale vapor molecules as the spacecraft passes through Europa's thin exosphere, or a plume analyzing their atomic composition, carbon dioxide, methane, ammonia, even complex organics. SUDA will do the same with solid particles catching ice grains that strike its target plate at thousands of kilometers per hour. Each collision becomes plasma, each plasma a code. Decoded, those flashes reveal salts, minerals, and perhaps the faint chemical accents of life. Every flyby becomes a ritual. The spacecraft will dive low sometimes, less than 25 kilometers above the surface, collect its data, then retreat back to the safety of distance before Jupiter's radiation can scorch its circuits. Over dozens of encounters, a pattern will emerge. Maps will grow denser, spectra sharper, models more certain. Europa will stop being a rumor. The plan is not to prove life, it is to measure possibility, to build the clearest profile yet of a world balanced between stillness and change. If the data align, if the ocean's salinity, the heat flux, and the chemistry all point towards stability, then Europa will become the first true candidate for an inhabited ocean beyond Earth. But even if the results are ambiguous, Europa Clipper will have done something profound. It will have transformed curiosity into precision. It will have turned a whisper into a map, and it will have paved the way for what must come next, the descent. For now, this mission is not about touching the ocean. It is about listening to its pulse from orbit, about tuning our instruments to rhythms too faint for the human ear, and realizing that those rhythms, though alien, feel familiar. Like breathing, like patience, like the slow heartbeat of something waiting under ice. If Europa Clipper is a solo and American melody of precision and endurance, then JWST is its harmony, a European symphony written for a choir of worlds. Its full name is Jupiter Icy Moons Explorer, and its mission extends beyond Europa. It will also study Ganymede and Callisto, mapping the diversity of Jupiter's frozen realm. But in that vast composition, Europa remains the first movement, the overture, where water magnetism and light begin their quiet dance. Launched by the European Space Agency, JWST represents a collaboration across continents, languages, and generations. It is Europe's answer to a question humanity now asks together. What does it mean when oceans exist in the dark? Where Clipper will orbit Jupiter in sweeping ellipses, dipping close to Europa dozens of times, JWST will perform only 2 flybys, brief, elegant encounters, at distances of just a few hundred kilometers. But even in those short passages, it will record more detail than any instrument before it. At the heart of JWST lies its radar for icy moons exploration rhyme, a cousin to Clipper's Reason radar, but tuned differently like a lower note in a shared chord. While Reason will probe deep, rhyme will listen shallow, focusing on the upper crust, mapping fractures and buried lenses of water no more than 10 kilometers beneath the surface. This duality, deep radar from Clipper, shallow radar from JWST, is by design. Together they will give us a full acoustic portrait of Europa's ice shell, from the cracks we can see to the caverns we can only imagine. But JWST carries another kind of sensitivity, one that listens not to structure but to light. Its MOLGIS instrument, the Moons and Jupiter Imaging Spectrometer, will capture reflected sunlight across hundreds of wavelengths, revealing the chemical soul of the ice. By studying how that light scatters and absorbs, MOLGIS can identify salts, organics, and ices of varying grain size, each a clue to how the surface has evolved. If it finds signs of freshly exposed materials near chaos terrains or plumes, that will confirm Europa's interior is still communicating with space. The mission also carries the JMAG magnetometer, designed to sense how each moon interacts with Jupiter's vast magnetic field. In Europa's case, this is more than academic, it's the best way to probe the hidden ocean indirectly. When Jupiter's magnetosphere sweeps past, it induces a counterfield within any conductive liquid below the ice. By measuring that distortion, JMAG will refine our understanding of the ocean's depth and salinity. It will do for magnetism what sonar does for sound, reveal shape through resonance. And because JWST will eventually orbit Ganymede, another ocean world, it offers a comparative lens, 2 moons, both icy, both with subsurface oceans, but one small and one immense. By studying them together, scientists will learn whether Europa's restless chemistry is unique or part of a grander pattern, an orchestra of worlds, each humming with its own internal energy. There is also symbolism in JWST's trajectory. It will reach Jupiter years after Clipper, perhaps crossing paths, indirectly sharing data through the vastness. NASA and ESA scientists have coordinated so their instruments complement each other, the same region seen through different eyes, the same mysteries examined from separate orbits. It is a reminder that exploration at its best is not competition, but chorus. We do not explore alone, we resonate. From its distant vantage, JWST will not simply confirm what Clipper finds, it will extend the question. It will look for global context for how Europa fits within Jupiter's magnetic symphony. And later, when it settles into orbit around Ganymede, it will carry Europa's lessons forward, tracing how oceans evolve when protected by magnetism rather than assaulted by it. In this way, JWST completes a story that began long before launch, a story of shared curiosity. The instruments, the scientists, the agencies all form a single consciousness stretching across worlds. When its radar pings the ice, when its spectrometer reads the light, it will not speak in accents of nationality but in the universal grammar of discovery. For in the end, JWST is not just a spacecraft. It is a symbol that the search for life wherever it leads belongs to all of us. And as it glides past Europa for those few luminous hours, it will carry with it the collective hope of a species listening together in the dark. When Europa Clipper has finished its long ballet around Jupiter, when its sensors have mapped every fracture and tasted every plume, another kind of mission will begin, one that trades orbit for descent. It will not circle from afar, it will fall deliberately through the silence. The concept is simple and terrifying, a lander hardened against radiation and cold settling onto Europa's surface, near a region where the ice may be thin. Its first act will be stillness listening. Seismometers will tune to the subtle groans of shifting crust, radar will look downward, and cameras will record a horizon unlike any other blue-white plains glittering under Jupiter's ghostly light. Then a deeper instrument will awaken a cryobot, a melting probe that will slowly burn its way down through kilometers of ice, carrying a thread of fiber optics behind it like a nerve reaching home. The cryobot's tip will be warm, its sensors relentless. It will map the changing density of the ice, measure temperature, chemistry, and salinity, and detect the faintest vibrations of motion beneath. Days will pass, perhaps weeks, as it sinks through a labyrinth of frozen layers until one day resistance will fade. The ice will give way to fluid. After centuries of theory, a human-made machine will touch an alien ocean. Then comes its companion, the Hydrobot, a miniature submersible released into the abyss. It will carry lights, cameras, and sensors drifting silently in a black sea that has never seen a surface, never known the sun. There it will search not for spectacle, but for movement. The curling of minerals, the shimmer of particles, the faint chemical pulse of something self-organizing. If such a mission succeeds, it will mark a new era. For the first time, our machines will swim in a world beyond Earth's skies. The dream that began with Galileo's telescope will end and begin again in water, and perhaps somewhere in that lightless ocean, Europa will answer with its own kind of reflection. To touch another world is to risk changing it. Every bolt, every sensor, every trace of oil from Earth carries the memory of life microbes that cling to metal molecules that persist even in sterilized air. And Europa, if it harbors its own fragile chemistry, must not become contaminated by ours. So before any lander is launched, engineers and ethicists work together under a shared vow: do no harm. Sterilization becomes a ritual, instruments baked, irradiated, scrubbed of their history. Even the cryobot's warm descent is modeled to ensure no terrestrial organism could ride its trail. Because a single microbe misplaced would not just endanger Europa's purity, it would compromise the truth itself. There is a second vow, quieter, but just as binding, to respect what we find. If the ocean proves lifeless, it remains sacred in its solitude. If it proves alive, we will have met something that never knew us, a separate experiment of the cosmos. And when that day comes, our task will not be to claim it, but to listen. In the end, every mission, every radar pulse, every whisper of data is not just about Europa. It is about us. Our longing to understand what it means to be alive has taken shape in circuits and metal, in the patient flight of machines through darkness. We have built instruments to look outward, but what they truly measure is the depth of our own curiosity. When Europa Clipper finishes its orbits, when JWST glides past in silence, we will hold more than spectra and chemical ratios. We will hold a reflection, a mirror suspended in Jupiter's light. Beneath that ice, whether there are microbes or only molecules, we will find a truth that belongs to all worlds. Where energy moves through water, the universe remembers how to organize itself. The search for life on Europa has never been about conquest. It has been about recognition of the same creative principle that shaped us still at work in the farthest cold. Even if the ocean lies empty, it will remain sacred, because in that emptiness, chemistry still strives toward meaning. And if we do find life, even a single cell, then the distance between worlds will vanish, replaced by kinship. One day, long after our machines fall silent, the data they sent will still echo. Children not yet born will listen to that echo and know that we reached across the void not for survival, but for understanding. Because to search the dark is in its quietest form an act of faith that knowledge itself is a form of light. Europa waits beneath its frozen sky, its ocean unbroken, its silence complete. But in that silence we have already heard an answer.